Welcome back. Today we're going to look at some of the alcohol synthesis and some of the reactions that can happen with alcohols. Now we won't get all the way through them in this video, but we'll get it the way. See, so some of them are going to be a review. Some of them will be new. Start with nucleophilic substitution. The basic concept, remember, is that we have a leaving group. Whoa. Leaving group, usually a halogen, and we add a nucleophile, being hydroxide. We do that, that can very easily form our alcohol. Remember, if it's SN2, we're going to see inversion of stereochemistry. If it's SN1, we're going to see a mixture. We have ways to add across the alkene. So if we do just a standard alkene, we could do acid catalyzed hydration. Catalyzed hydration. At this point, form alcohol. This is our Markovnikov's addition. We could also do oxymercuration, demercuration, which is where we use the mercury acetate. And then, what if I remember right, sodium borohydride. And this is also Markovnikov addition. All these guys. We also have hydroboration. Hydroboration, which hydroboration oxidation, so that's where we use the BH3. And then peroxide. And this guy is anti-Markovnikov. So this guy would have a anti-Markovnikov addition. That's because the boron is the electrophile, the hydrogen is not. Hydrogen is part of the nucleophile. And then we remove the boron with OH. There's also syn addition. So that's also syn. Remember, syn, or anti. Syn, it's adding to the same side, the same face of the double bond. We can also have ways adding two oxygens to form dihydroxy ones. You can have osmium tetraoxide, and then we use a oxidant such as H2O2 or permanganate to form our dihydroxy. This is syn addition. But we can also use epoxide, like use our metachloro peroxybenzoic acid, MCPBA, followed by acid. This guy is anti-addition. So there's various ways to do that. All those went over a little bit on the alkene chapter. We can also react with alkyne. So I see. Oh yeah. Well, we have alkyne, well not alkyne, but alkenyl anion can attack a ketone. Then in the presence of water or an acid, we can form an alkenyl alcohol. In this case, if I'm attacking a acetone or something like that, ketone, would forming a tertiary alcohol. Now, there's also a series of Grignard reagents. Now, what is Grignard? If you haven't already heard of this, Grignard reagent is what? Grignard is some sort of alkyl anion that we make when we mix the alkyl halide with magnesium to form this really strong, really powerful nucleophile. This nucleophile will attack any acidic region, whether this is a Lewis acid or just a Arrhenius acid or Bronson-Laurie acid. It will attack any sort of acidic region. For this reason, we need to be very careful. This can only work in dry aprotic solvents. That means water. Water is polar. Water is acidic. Water will neutralize this and deactivate this. So the basic idea, how you form this, take this, you add some magnesium. We can do this in, say, diethyl ether. And you form RMG with D minus, D plus. But essentially, when we look at this, this is just a R minus and a MGX. Compound. Now, this will form with most halides, but it works best with the bigger, the heavier the halide. So RI would work better than RBR. Easier to form RBR. Which would be easier to form than RCl. But regardless of which, RF is particularly hard to form. Mainly because the RF bond is going to be very strong. very hard to break apart. Now, this R group could be anything. Could be a ring. It could have other functional groups on it, as long as those are not acidic functional groups. Could be a primary carbon, a secondary carbon, tertiary carbon, a vinylic carbon. Could be an aryl halide. So we can do this with say X. We can replace that. We can put the magnesium in there. We could slip that in there. All of these are valid R groups that can be put in there. The only thing is, once again, you have to make sure there's no acidic portions. If there's an alcohol on that R group, that alcohol is acidic. The reaction will self-react and neutralize itself. And so that won't work. You could also form a similar thing with organolithium, where ether isn't necessary, but it works a similar way. Rx plus 2 equivalents of lithium will form 1 lithium halide and 2 R lithium, some alkyl lithium, organolithium, which is essentially, once again, R minus and lithium plus. The lithium is stabilizing and these create very strong nucleophiles, very strong bases. So what happens when we have these Grignards and these organolithiums? Well, what happens is your R group, Mg, it reacts very similar to that alkynyl anion we saw earlier. So R, this guy is going to go swinging through and attack this really strong electrophile. And these lone pairs are going to be kicked up. We're going to form this intermediate, R prime, R, O minus. Now, once we've formed this, and we completely used up the Grignard, well, actually, when we completely used up our ketone, we can add water or acid, and this will serve 2 purposes. So, 2 purposes. Purpose 1 is it will pronate your alcohol. You have a tertiary alcohol at this point. Purpose 2, it will deactivate the rest of the Grignard, so you don't have to worry about that. So a ketone will form a tertiary alcohol, but we can do this with the aldehyde to form a secondary alcohol. We can do this with formaldehyde to form a primary alcohol. So depending on the R groups, formaldehyde is no R groups, so you could form a primary alcohol with that. So depending on the R groups and the H groups, we can form a tertiary, a secondary, or primary alcohol. Now, continuing this line, we could also add twice in certain cases when we have good leaving groups. A hydride is not a good leaving group, but when we have acid chlorides and esters, and ester, the alkoxide and the halide are good leaving groups, and so we'll see a double addition. Double addition. How does that happen? So let's look at the acid halide. acid halide, so let's just chloride RMGX. This attacks here, kicks that up. We form our intermediate. So black chloride. Minus. So from here, this is a rather fast step. The lone pair on this negative charge swings back down to reform the double bond, kicking off our leaving group. And so we reformed a ketone. We reformed our ketone, which then another equivalent of our Grignard can attack again, causing the shift up. And there we have a double addition of our R group. So in this way, we can add two equivalents of our Grignard. And then, of course, water or acid to fully form the alcohol. Now, this is very similar for esters. It's very similar for esters in that instead of chloride as a leaving group would lose whatever the OR, essentially the alkoxide. We can also do this with epoxides. Epoxides are particularly strong electrophiles because of this ring strain and what have you. Let's see. Grignard, being a nucleophile, will react and ring open. So attack here and cause this to swing open, releasing our ring strain. So you're going to have a I've gone to minus, and of course, presence of acid is going to just protonate that. Now, which way is it going to attack? It's going to attack the reason. It's going to attack essentially to ring open, create which carbon can better hold the negative charge. Keep that in mind. Which carbon can better hold that negative charge, help hold that electronegative oxygen. So it will attack one versus the other unless it's symmetrical. Now, Grignard will not react with alkyl halides. So you're not going to swap these around. We're not going to be able to get, this does not happen. Where we have R prime X. We're not going to have R. That doesn't happen. So this typically attacks with strong electrophiles, not just your basic ones. We're not going to have nucleophilic substitution. We're going to actually attack a ketone, aldehyde. So those are very strong Lewis acids, or say epoxide. Now another one that works on a similar method is the Gilman reagent. This is a modification of our organolithium. Gilman reagent. This is a special one. So we take, first we have to take our organolithium, and then we're going to add in copper iodide, form R2CuLi. and of course another Li. Now, why is this Gilman so special? This Gilman is special because that is how we are going to add and replace the alkyl halide. With our Gilman, we can add to an alkyl halide, R prime X, R. It reacts similar to SN2, but through a different mechanism. So we're not going to relearn the mechanism. But so this is one of the ways to do it. So if you want to add these together, what are you going to do? So if I want to add R prime to R, we're going to start with R prime X. We're going to mix in first step 1, 2 equivalents of lithium, and then step 2, copper iodide to form our prime CuLi. And then on the third step, we're going to add our alkyl halide that we want to react. And bada boom, bada bing, you can snap these together. Now, why are we doing this instead of, say, SN2? Well, it allows us to add it allows us to make unusual carbon-carbon bonds. We're not adding a nucleophile, we're adding 2 carbons together. You can snap together 2 vinyl groups. So if this was my starting product and say this was my step 3 product, we've now created we've essentially found a way to snap together a ethene with a propene. And one other thing is that Gilman does not react with carbonyl. So our R2CuLi plus no reaction. It's a way you can selectively add to this. However, we can add this to acyl halides. So R2CuLi, if I add this to acyl chloride, what am I going to get? We're going to replace the halide, not make an alcohol. So it's going to stop at a ketone, not go all the way to an alcohol like we would if we had a Grignard. So it only replaces the halide, nothing else. That's kind of neat. Now, so there's some side reactions of the Grignard we have to worry about. Grignard or the organolithium. In the presence of water, it's going to just fully reduce. It's going to form RH. We're going to neutralize our thing and we're going to form. But this is a convenient way to go from RX to RH. If we need to remove the halide and replace it with hydrogen, we can do that just by forming organolithium or Grignard and then adding water. Let's see. Grignard can also attack other multiple bonded electrophiles. So we already know that Grignard and organolithium will react with a ketone, but it will also react with a imine will react with a nitrile, and it will react with SO2, and it will react with, some of these are a little bit less common, nitroso. We'll get to some of these a little bit later. Some of these we may not cover. Now there's a couple other things we can do. There's we can also do some reduction of carbonyls to alcohols. Reduction some of these compounds we've already seen a little bit already. We'll have the hydride additions. The two most common ones are sodium borohydride. We've seen that one used in the mercuration, demercuration. There's also lithium aluminum hydride. If you notice, sodium, lithium, same column. Boron, aluminum, same column. These are 3 electron guys that essentially could not have an octet until we add an extra hydrogen. So the basic premise here is we add the aluminum hydride. It's negatively charged, where it allows us to add a negatively charged hydrogen, because hydrogen typically less electronegative than most things, except for, say, aluminum. So the negatively charged, we can add it here, swing it up, and then you form some form of hydrogen, O minus, which is then attracted to the lithium. And then we have aluminum hydride floating around. And then in the presence of water, bada boom, bada bing, we have a secondary alcohol. So a ketone can be turned into a secondary alcohol in that way. Now the reactivity is that lithium aluminum hydride, so smaller metal, smaller metal, bigger middle thing, is more reactive than sodium borohydride. And so this will provide some selectivity, because some of these will only work with certain classes. So lithium aluminum hydride is more reactive than sodium borohydride. The same way that hot concentrated potassium permanganate will completely oxidize, but cold dilute will only partially oxidize. So in the classes of compounds that will react, we can have out here a esterate, well, essentially like acetate, essentially like acetic acid. We could have a full ester, neutral ester. We could have a ketone, and we can have an aldehyde. These guys are, as we go up in the scale, these guys are less and more reactive. Aldehyde is the most reactive. This charged ester, this acetate or whatever, is less reactive. So sodium borohydride will only react with our carbonyl group. If there's another alcohol there, it will not react. But lithium aluminum hydride will react with all of these. And fully reduced. So if we wanted to, say, avoid overreacting, you would choose which one you have. So, and for example, an ester would first, with the first addition of lithium aluminum hydride, puts it into a similar situation as the Grignard. We have R, we have H, O minus, and we have a good leaving group. A good leaving group. So what happens is swings down, reforms the double bond, leaving group leaves. And so then we can add another equivalent of the lithium aluminum hydride, and it's going to keep adding, and it's going to kick it down from a ketone, or sorry, from an aldehyde all the way to a primary alcohol. And you may say, well, Andrew, then why don't we just add less lithium aluminum hydride? Well, then the problem becomes aldehydes are still more reactive than an ester. So the second you reduce the first guy down to a aldehyde, you're going to react that fully to conclusion. So if you added less lithium aluminum hydride, you would not get the intermediate aldehyde. You would simply get less product. You would have less converted ester because of that. So you cannot stop this prematurely. Okay. There's a few other things I'll go through, like I think one more example, and then we'll be done. And that is hydrogenation with a Raney nickel. Raney, R-A-N-E-Y, nickel catalyst. It's a special type of nickel aluminum alloy. It's a nickel aluminum alloy that will allow, it's been treated with hydroxide. So what this is going to allow us to do is to hydrogenate ketones and aldehydes in addition to our standard alkenes. So if I had a compound like this, and I used excess hydrogen, we'll just put two equivalents, and we used Raney nickel as opposed to our usual platinum, we would fully reduce this down to a alcohol. As opposed to if I did platinum, it's just going to be so that is all the various reaction ways we can synthesize alcohols. There may be some more coming up, but the next video we'll look at chapter 11, which is going to be the reduction, sorry, not the reduction, but the reactions of alcohol. So what type of reactions can occur. So thank you for your time. Have a good day.